So my topic is diabetic retinopathy detection using EfficientNetB0 and Grad-CAM visualization. So myself, Koushika Priyadharshini, research scholar, Anna University, MIT campus. So diabetic retinopathy is a leading cause for blindness among working adults. Early detection is essential to prevent irreversible vision loss. Manual examination of the fundus image is time-consuming and subjective. It also requires specialized medical expertise and consistent grading. So deep learning model can standardize and accelerate this DR diagnosis and also reduce human error and support large scale screening. And the proposed system not only detects DR but also diagnoses its severity across 5 clinical stages. So this helps in prioritizing the treatment and monitor disease progression effectively. So the proposed model is efficient at BO for DR classification and Grad-CAM for interpretability. So the problem statement are: first, DR requires timely and accurate diagnosis to prevent vision impairment. Secondly, manual grading is labor intensive, subjective, and not scalable for large population. Thirdly, lack of automated tools to detect and classify DR severity hinders early intervention. So the objectives are to develop a DL model using EfficientNetB0 for classification of DR stage from the retinal image, to automate the detection and severity diagnosis of DR into 5 clinical class. Thirdly, to apply image augmentation technique for improving model generalization and performance. Finally, to use Grad-CAM for visual explanation of the model's prediction, ensuring transparency. So the proposed model architecture. So I've taken a data set that has both normal and DR affected images. I'm combining them. I'm splitting that data set into two parts, training and testing. So the testing is 20% and training is 80% of the data. Now I'm going to pre-process it. So I'm doing flipping, translation, rotation and resizing. So these are, so the flipping part, translation and rotation part are because my model needs to be exposed to variations, and I'm doing resizing because the image can be of any height and width. So I'm fixing the image height and width into 244 into 244. And this is my proposed model architecture's process. So after the pre-processing, I'm giving the input to pre-trained model. So this model is a pre-trained model wherein weights and biases are fixed. Now I'm removing the top layer part and adding custom layers in order to increase the learning process of my model. And now I'm going to do the training part. After training, my model has been trained. Now I'm going to give testing data and record the predictions and evaluation. Here I'm using Grad-CAM. So what Grad-CAM does is it tells what are the pixels that are responsible for my model to predict that for my model's prediction. So for example, I'm taking an image from severe class, and I'm trying to give that to my model, and my model is predicting that it is a severe class image. It is an image from the severe class. So my Grad-CAM will tell what are the pixels that are responsible for my model to predict that this image belongs to severe class. So that's what Grad-CAM does. It shows by using heat map. So this is the proposed model architecture. These are the layers that will be in the pre-trained model, where after convolution 1 cross 1, I am removing all these layers, adding my custom layers, wherein it will have global pool, average pooling 2D, and then dropout, and then dense, followed by dropout. This is because my model needs to converge fast and also stabilize training. And at the end, I'm adding softmax activation function to this dense, because since it is a multi-class classification problem, I'm doing that. So all that said and done, I'm going to my data set part. I'm using this Aptos 2019 blindness detection data set. This is available in Kaggle, and there are 3,662 images of different severities, of different severity classes. So these are the image distribution. As you can see, the data are distributed, and my data set is imbalanced, right? So for this, I'm using class weight method. So class weight based balancing. So what I'm going to do is, if I'm going to give an image from this third severe class, and my model is predicting it as some other class, then I will impose more penalty for that. So the loss that I give, the penalty that I give for this and this, comparing to that, my this loss will be high. So my model will understand that if there is an image that is coming from this class, I have to predict right, else there will be more loss. Since my model aim is to reduce loss, so it will predict right. So this is what class weight based balancing. So this is my sample data set. So I'm doing EDA. So I'm trying to visualize my class distribution. Followed by that, I'm balancing it by class weight method. So as I said before, and also I'm trying to view my image width and height after pre-processing. So it is 244 into 244. This is my algorithm part, wherein I am trying to take the input of retinary images which are labeled from 0 to 4, and the output will be predicted diabetic retinopathy stage and visual mode interpretation. So first initially I will load the data set, perform data pre-processing and augmentation. Followed by that, I am converting my image data into NumPy array for model training, and then performing one-hot encoding for class labels and for identification and aging. So followed by why I'm doing this is because initially my class labels would be in text format, so I'm converting it into a numerical for my model to understand. Then I am performing model building and model building. So adding custom layers, removing the top layer, performing train test split, training my model. Followed by that, I'm testing my model. So followed by that, I'm doing Grad-CAM visualization. So here I'll tell how this works. So before I told what is it, why I'm using it. Now I'm telling how it will work. So it will compute gradients. So here I will take the feature map that comes out of the model at the end. So when after after all the model training, if I pass an image into my model will have a feature map, right? So I will make use of that feature map and give it, I mean, the gradient cam will make use of that feature map. Now what it will do is, it will take the original image, compute gradients between the feature map and the original image. Pixel by pixel, it will create a matrix. So from that we'll get to know what are the pixels that are responsible for my model to predict so. So it will show the pixels by using heat map, like it will highlight the regions by using heat map. So these are the methodologies. So followed by data collection, EDA, data augmentation and pre-processing, model development, training, and then explainability by using Grad-CAM, evaluation and validation. So these are the set of modules. First, data pre-processing and augmentation, followed by model building and training, evaluation and Grad-CAM explainability. So this is the sample image from each class. So this is the model accuracy over epochs. In here I have plotted training accuracy and validation accuracy. Again here I have plotted training loss and validation loss. Followed by that, this is my classification report. So after testing, I'm trying to print the classification report. So wherein I got my model as predicted 76% with an accuracy rate of 76%. So given an original image, my model will tell the confidence score, that is how much it is predicting each class, like what is the class of that image. Based on confidence score, we'll get to know. And this is a superimposed Grad-CAM. So these are the areas that were responsible for the model to make this prediction. So it is like the red one will be more influenced than the yellow, than the green. So these are the regions that are responsible for my model's prediction. So I've compared with various proposed model, comparing my proposed model accuracy with various other models. So mine is giving 76%. So let me explain the coding part. So any person who is affected by DR will have any of these abnormalities, like abnormal blood growth or vessel growth, and then this clotting of blood, and then cotton wool spots, and then hemorrhages. So something like this will happen, and it will lead to vision loss. So Firstly, I have imported all the libraries. Then I have imported the data set from Google Drive. Then I have set the image size, batch size, number of classes, epochs, and seed. Now I am trying to do EDA, so to see how my images are distributed. So I am using class weight balance for balancing them. Then this is the sample image from each class. I am doing a training test split. So that is 20% for testing and remaining for training 80%. And I have done data pre-processing like rotation and flipping. Followed by that, I have resized my image. So here I am trying to view my height and width of the image after resizing. And then here I am trying to define my model. So I am removing the top layer and trying to add these custom layers. I've used model.summary for showing the structure of my model, and I'm trying to show it in the visual way. And then training comes so I'm using class weight based balancing. And then here instead of verbose, I'm using callback. And I have done model fitting. That is, I've trained the model. So there are 24 epochs. Totally. So I'm trying to plot the accuracy and then loss. So finally, I've printed my classification report wherein that is 76% accuracy. I'm trying to visualize my prediction, like giving. Sorry, I'm trying to visualize how my model is predicting. So given some random images, I will see how my model has predicted. Say I have taken this image. So my ground truth was moderate, and my model has predicted it as moderate. So this was the original image, and after Grad-CAM imposition, it shows that these are the this is the area, that is the pixels that were responsible for my model to predict it as moderate class. So another example wherein the ground truth was severe and my model has predicted severe. So original image, this is the original image. After superimposed Grad-CAM, it shows that these were the regions that were responsible. So you can see these blue spots. So these were the region. So that's why my model has predicted as severe. So this was all about diabetic retinopathy detection using EfficientNetB0 and Grad-CAM visualization. Thank you.